Hello everyone. Today I'll be telling you about how to do a proper designing, what should be the approach, and how it's gonna help you to design a better component, as well as it will be really helpful in manufacturing purpose also. I'll show you the paddle design, how it's going to design. Basically I'm really good in parametrics, so whichever software do you use, it's good. It's all has the same function. You can use any software. So I have already created the paddle. uh, the basic objective of paddle design is, you can see on the internet that what is the optimum design, so accordingly you can choose the design. I have chosen it's gone I had chosen the configuration having this one. Yes, I have chosen this configuration, 2 inch and 12 inch. Okay, so I have already designed this paddle. Let me show you. Yes, this is this is the basic model, not the accurate one. And what is the basic objective is that first you need to design it, and after that you need to calculate the loads that comes from the applied pressure or applied force by your foot, and the reaction force from the piston rod. So after that you'll get the load calculations, and after the load calculations you can analyze this paddle, and accordingly you can modify the design to reduce the weight, right? So this is the pedal. Now I'm going to do the assembly, right? So I'll open the assembly directly. So yeah, this is the assembly I have already created, in which as you can see, this is my pedal. This is a push rod. I have provided, this is my default, so it won't be moving. It's like a rigid structure. It's this hole is a pin joint, this hole is also a pin joint, and between this pin joint and this one I have provided the damper, right? So basically it will move like something. Let's hang. Yeah, it's moving. It'll move like something like this. Okay, so let's start with the analysis. Don't close. It's really slow, all after it's a design software. Okay, so Here's the assembly part. So now I'm going to do the analysis, which is a dynamic analysis. I'll go into mechanism, then I have some constraint over here, like I have applied a force on this pedal, and here's the damper between this and this. Here's the pin joint, here's also pin joint, and force, then damper, and I have given some value. It's arbitrary value, right? It's 100 Newton second per mm, and the force I have applied is also arbitrary. That's 100, right? So now let's start the analysis. Run. It's running, as you can see here. So it's basically what it does. It is calculating all the positions of the all joints and giving the reactions, right? It's a dynamic analysis. Let me show you. I'm enabling the gravity over here, and it's a frame rate. You can select up to whatever accuracy you require. If you require higher accuracy, you can select 100 or more than 100. It'll give you a better result. Now let's check out the results. Okay, so we'll measure. What we're going to measure is we'll measure the reaction force due to this damper. So I'll go in connection, reaction, radial force exerted on body. When this is a highlighted body, how much force is going to exerted? It's already selected, and OK, apply, and OK. Right, I need to select this one. Okay, force in right direction. It's not selecting. Connection, radial force exerted on body 2, exerted on body 1. Apply. Okay, that's not keen. So it was like I need to select the entity. I have selected this point. It will give the reaction force on this point due to the damper reaction. So let's check this value. This is my analysis result. Yeah, so basically I'm getting this value. Let's show the graph. Yes, it's a graph over here, and as we can see, maximum value we are getting is 1.09 into 10 raised to 8 Newton per centimeter square. So if we want to check on which point is giving us the higher value, we can check from the motion, right? As you can see, it's still calculating. If you have selected 10, then it'll take a huge time, right? So now let's check this. Okay, as you can see, this red. So when the piston, we are pushing the pedal, at this moment it's it's giving us the maximum value, which is the force is exerted on this pin joint, right? So this is the force value we got. So based on this, we need to do the static analysis. You can do this in any software, Hypermesh or ANSYS or whatever software you are comfortable with. So this is the value. This is 1.096 into 10 raised to 8, right? So now we'll go to the analysis part. Let's close this. Okay, so I'm using Inspire. It's a really good software. It gives us the also the optimum value. Also, it shows the graphs, not the graphs, but it shows the model from which we can remove the excess material, right? So I'm importing this one, this file. So basically we need to do a mirror of this because it's the geometry is not completely satisfying this student version. I don't know, so I'm making a mirror, and the system is really slow. Okay, I have created the mirror part. It'll take time. So mirror part is created. Now we'll move to the analysis part. So here I am in the analysis part. So let's apply the support reaction. It will be over here and over here. Okay, and I'll apply the load on this portion, which will be the pedal force. It will be in the Z direction. I'm applying arbitrary value about 100 Newton. Okay, so here the load will not come, so let's remove this part. Instead the support, not load, support, it will come the load that we got from the mechanism result. I'm applying this much, the arbitrary value. Now we'll analyze the structure. Okay, so faster and run. So it'll calculate the von Mises stresses that which we can check for our material that it's safe or not, and how much factor of safety that we require. Okay, analysis done and view now. Okay, so it's a von Mises maximum. It's 0 0. It's showing 0 0. It's because we have taken the arbitrary value. We can take more, like the force value, delete, and set direction. Let's say 10,000 Newton. Okay, and Let's run it again. Okay, so still we're not getting the values. I don't know. Displacement we are getting, or maybe material is not assigned. Let me check. Oh, it's design space. I really forgot that. It's a design space. Okay, so let's check the material. Material is we can select AISI 1040 null show the result. We need to be really careful about all the inputs. The inputs will give based on that will get the output. Okay. Okay, so it's done. Let's view now. Still we are not getting. Maybe something is wrong. I think this is the not the correct. I need to give a support over here, right? We are checking the static condition, not the dynamic condition. So it's a support over here, not the force we are applying. Okay, and now let me check again. Really forgot the input that we are testing the static, not the dynamic. Oh, still we are not getting the values. Something is wrong. Something is wrong. Let me check. Maximum principal stress we're not getting. Not getting even the deflection. Let me correct the load value. What's that? Delete. I need to apply it over here because it's a pin joint and it won't define a pin joint. Need to apply over there. Okay. Basically we need to create a point Joda. I'm only applying on the I'm not applying on the circumference, I'm applying in the air, so I think it won't calculate. Oh, so now I'll just say that we were applying on the whole part, right? So we need to be really careful. So I'm getting the maximum value over here, which is 1.15 into 10 raised to 8. We can check this, right? We can check the material property, right? www.efunda.com. Search manager. Okay, it's AISI 1040. One alloy found, AISI 1040. Its maximum value is yield strength is 253, right? 253 its yield value. After that the elastic zone will start, so material won't return to its original state. It's 353 MPa, 353 into 10 raised to 6, and we're getting 1.50 into 10 raised to 8, so 0.01, which is lower than this. So basically our calculations and our material is not correctly defined, so we are not getting the exact value what we are required. So this is how you can check the static analysis, that your thickness, your width, and your dimensions are correct. So Now it's about to do the optimization. Right, so what are the portion that we can remove from the material? Right, it's about weight reduction. We can simply optimize this, and we can remove the excess material from this. So it's calculating our showing error. mm, I don't know why it's showing the error. Let me check. Okay, so basically the similar problem occurred. I applied the supporting error, so we need to be really careful. So from this we can see that how much portion uh, we can remove, right? This much we need to let me select the 5% part and then run again. Okay, so as you can see from this result, it's saying that we can remove the material from over this part, so it won't affect the stiffness and strength of the material. So we can reduce the weight by putting some hole over this area, holes over this area and this area, right? So that's basic the objective. Now again, accordingly design it, and then do the mechanism analysis again, then again do the this analysis and optimize it, and after that it's good to go. Now make a manufacturing drawing and make a file, and after the selection the file you have made for the different component, it will be really helpful to fastly manufacture your all the component with the accuracy. So at the time of manufacturing you won't be required to see that it will gonna sustain this situation, or it will not going to sustain the situation. So this is the basic design procedure. we cannot we cannot just simply put the any load on this point and anything, right? Even in the roll cage analysis there are certain points and certain constraints we need to consider, like gravitational force, why we are taking a 5G force. All that we need to understand, and from that we need to apply, right? So that's it. Thanks.